In December of 1900, a physicist in Berlin did something he would spend the rest of his life trying to take back. Max Planck, a conservative man by every measure, cautious, methodical, deeply uncomfortable with radical ideas, had been working on a stubborn problem in thermal radiation. The mathematics refused to behave. Classical physics predicted that a hot object should radiate infinite energy at short wavelengths, which was obviously absurdly wrong. So Planck tried something he considered a purely mathematical trick. He divided energy into tiny, discrete packets, not because he believed energy actually came in packets, but because it was the only way to make the equation work. He called them quanta. He expected someone would eventually find a way to smooth them back into the continuous physics he trusted. No one ever did. That single act of mathematical desperation, reluctant, provisional, almost embarrassed, cracked open a door that could never be closed. Within 3 decades, the entirety of classical physics would be overturned. The universe, it turned out, did not work the way anyone had imagined. Not at the smallest scales. Not even close. This is the story of how we found out. From Planck's unwilling revolution to the fierce debates that still divide physicists today, this is the history of quantum physics, told through the people, the experiments, and the ideas that changed everything. Welcome to Quantum Questions, where we do exactly what it says on the tin. Questions about all things quantum, explored with the depth they deserve. If that's your kind of thing, please consider liking and subscribing. To understand what Planck did, you first have to understand what he was up against. By the late 1890s, physics had a problem it could not solve. And the problem was light. Not light as it travels through space or bends through glass, but light as it radiates from hot objects. Everything that has a temperature emits radiation. A warm body glows in the infrared. Heat it further and it begins to glow red, then white. The spectrum of this radiation, how its energy is spread across different wavelengths, follows a pattern so universal that it does not depend on what the object is made of. A block of iron, a lump of carbon, a sealed oven with a tiny hole in one wall, all produce the same curve. The physicist Gustav Kirchhoff had established this back in 1859, and he posed a challenge to the field. Find the mathematical function that describes that curve. Find the law of thermal radiation. For 40 years, no one could, and the reason was not a lack of talent. Some of the finest minds in European physics worked on it. Wilhelm Wien, Lord Rayleigh, James Jeans. Wien produced a formula that worked beautifully at short wavelengths but collapsed at longer ones. Rayleigh and Jeans derived a formula from solid classical reasoning that worked at the long end but predicted something catastrophic at the short end: infinite energy. A hot object, according to their equation, should pour out unlimited energy at ultraviolet wavelengths and beyond. This was not just wrong, it was absurd. It became known later as the ultraviolet catastrophe, though in 1900 the full scale of the disaster had not yet sunk in. Planck had come to the problem through thermodynamics. He was a man of deep intellectual caution. He believed in the absolute certainty of the second law of thermodynamics the way others believed in scripture, and he had spent years trying to understand how electromagnetic radiation reaches thermal equilibrium inside a closed cavity. He was not looking for a revolution, he was looking for clarity. Then the experiments forced his hand. In the autumn of 1900, Heinrich Rubens and Ferdinand Kohlbaum at the Physikalisch-Technische Reichsanstalt in Berlin produced a new set of measurements. Their data covered the long wavelength end of the spectrum with unprecedented precision, and they showed beyond any reasonable doubt that Wien's formula failed. Rubens visited Planck at home and shared the results directly. That same evening, Planck sat down and, almost by interpolation, fitting a curve between Wien's law and the Rayleigh-Jeans limit, arrived at a new formula. He presented it to the German Physical Society on the 19th of October, 1900. It matched the experimental data perfectly, every wavelength, every temperature. But Planck had no derivation. The formula worked, and he had no idea why. What followed over the next 2 months was, by Planck's own later account, one of the most intense periods of work in his life. He needed a theoretical foundation for his formula, and the only route he could find ran through the statistical methods of Ludwig Boltzmann, methods Planck had spent years opposing. Boltzmann treated thermodynamic quantities as averages over vast numbers of microscopic states. Planck had always resisted this. He believed the second law was absolute, not statistical, but now he had no choice. To derive his radiation formula, he had to count the number of ways a fixed amount of energy could be distributed among a collection of oscillators. And to make the mathematics close, he had to divide that energy into finite portions, packets proportional to the frequency of the radiation. He called these packets energy elements. The constant of proportionality was a number he designated h. He presented this derivation on the 14th of December 1900. It is often called the birth of quantum theory. But here is where the story gets complicated. Planck did not storm into the lecture hall believing he had shattered classical physics. He almost certainly saw the energy elements as a mathematical bookkeeping device, a way to make the counting work, not as a statement about the physical nature of energy. The historian Thomas Kuhn argued forcefully in 1978 that Planck did not intend a genuine quantization at all, and that the revolutionary reading was imposed retrospectively. Martin Klein, writing earlier, had given Planck more credit. The truth, as the physicist and historian Clayton Gerhardt later concluded, probably lies somewhere between the two. Planck introduced something radical. He just did not fully realize how radical it was. And that is what makes the moment so extraordinary. The door was opened not by someone who wanted to walk through it, but by someone who was simply trying to fix an equation. The idea might have stayed buried. Planck's energy elements could have remained a curiosity of statistical bookkeeping, a trick that worked without anyone asking too hard why. For several years, that is more or less what happened. The physics community took the radiation formula and moved on. Very few paused to consider what the derivation might actually mean. One person did. In 1905, a 26-year-old technical expert at the Swiss Patent Office in Bern published a paper that would do something Planck had never intended. Albert Einstein did not merely accept the quantization of energy, he extended it. In a paper titled, "On a Heuristic Point of View Concerning the Production and Transformation of Light," Einstein proposed that light itself, not just the emission or absorption of light, but the radiation field in transit, consists of discrete, indivisible packets of energy. Each packet carries an energy equal to Planck's constant multiplied by the frequency of the light. Einstein called them light quanta. This was a far more radical claim than anything Planck had made. Planck had quantized the oscillators that emit and absorb radiation. Einstein was quantizing the radiation itself. He was saying that a beam of light is not a smooth, continuous wave, but a stream of individual particles. This directly contradicted Maxwell's electromagnetic theory, which had been one of the great triumphs of 19th century physics, and which described light as a wave with extraordinary precision. To suggest that light came in lumps was, to most physicists at the time, deeply uncomfortable. Einstein's target was the photoelectric effect, a phenomenon that had been observed but never properly explained. When light strikes a metal surface, it can eject electrons. But it does so in a way that classical physics cannot account for. Below a certain frequency, no electrons are emitted at all, no matter how bright the light. Above that threshold, electrons appear immediately, and their energy depends only on the frequency of the light, not on its intensity. A brighter beam ejects more electrons, but each individual electron carries the same energy. A classical wave theory of light predicts none of this. The energy of a wave depends on its amplitude, not its frequency. There is no reason for a threshold to exist, and there is no reason for the energy of ejected electrons to be independent of brightness. Einstein's explanation was direct. Light arrives as individual quanta. Each quantum carries a specific energy determined by its frequency. If that energy is too low to overcome the binding force holding the electron in the metal, the electron stays put, regardless of how many quanta arrive. If the energy is sufficient, the electron is ejected immediately, with the surplus converted to kinetic energy. One photon, one electron. The relationship is clean, specific, and quantitative. The reception was almost universally hostile. Planck himself rejected the idea of light quanta outright and continued to do so for more than a decade. When Planck recommended Einstein for membership in the Prussian Academy of Sciences in 1913, he praised Einstein's work lavishly, then added a specific disclaimer about the light quantum hypothesis, asking that it not be held against him. Niels Bohr, who would soon build his own quantum theory of the atom, also refused to accept light quanta until well into the 1920s. The most striking resistance came from the American experimentalist Robert Millikan. Millikan was convinced that Einstein's theory was wrong and set out to disprove it through a meticulous series of experiments on the photoelectric effect. He spent roughly a decade refining his apparatus and his technique. When his results finally came in, they confirmed Einstein's equation with extraordinary precision. Every prediction held. Millikan published the data, acknowledged that the equation worked perfectly, and stated in the same paper that the theory behind it was, in his view, untenable. Einstein received the Nobel Prize in Physics in 1921. The citation was not for relativity, it was for the photoelectric effect, for his discovery of the law governing it. Even the Nobel Committee hedged. The prize honored the empirical law, not the underlying claim about the nature of light. The quantum of light was still, officially, too strange to fully endorse. It would take almost 2 more decades, and the work of Arthur Compton demonstrating that light quanta carry momentum as well as energy, before the physics community accepted what Einstein had seen in 1905, that light is not purely a wave. It is something stranger, something that behaves as both wave and particle depending on the question you ask. The word photon would not be coined until 1926, but the idea was there from the start. By 1913, 2 things were clear. Energy comes in packets, and light comes in packets. But no one yet understood what any of this meant for the structure of matter itself. The atom at that point was barely understood. Just 2 years earlier, Ernest Rutherford and his colleagues at the University of Manchester had fired alpha particles at a thin gold foil and found that most passed straight through. But a small fraction bounced back at extreme angles, as though they had struck something very small and very dense. Rutherford concluded that the atom's positive charge and nearly all of its mass are concentrated in a tiny central nucleus, with electrons orbiting at a distance. It was an elegant picture. It also could not possibly be correct. The problem was classical electrodynamics. An electron moving in a curved orbit is constantly accelerating, and a charged particle that accelerates must radiate energy. An orbiting electron, according to Maxwell's equations, should lose energy continuously, spiraling inward as it radiates, and crash into the nucleus in a fraction of a second. Every atom in the universe should be unstable. The fact that matter exists at all was, under classical physics, unexplained. Niels Bohr, a young Danish physicist who had recently spent time working in Rutherford's laboratory, proposed a solution that was as bold as it was strange. In a paper published in 1913, Bohr suggested that electrons can only occupy certain specific orbits around the nucleus, discrete energy levels separated by fixed gaps. An electron in one of these allowed orbits does not radiate. It simply stays there, stable, in defiance of classical electrodynamics. When an electron jumps from a higher orbit to a lower one, it emits a single quantum of light, a photon, with an energy exactly equal to the difference between the two levels. When it absorbs a photon of the right energy, it jumps upward. The audacity of this proposal is easy to underestimate from a modern perspective. Bohr was not offering a derivation. He was offering a set of rules, postulates with no deeper justification. Why should certain orbits be allowed? Why should electrons not radiate while circling the nucleus? Bohr had no mechanism, only the assertion that nature works this way. The justification was empirical. The model worked, and it worked beautifully. The specific wavelengths of light emitted by hydrogen, its spectral lines, had been measured with great precision for decades. Johann Balmer had found a formula in 1885 that described the visible lines of hydrogen's spectrum using a simple numerical pattern, but no one had ever explained why that pattern existed. Bohr's model explained it exactly. Each spectral line corresponded to an electron dropping between two specific energy levels. The frequencies predicted by Bohr's quantization condition matched the experimental data to within a fraction of a percent. For hydrogen, the agreement was extraordinary. For everything else, it was not. The moment physicists tried to apply Bohr's model to atoms with more than one electron, it struggled. Helium, the next simplest element, resisted the approach almost entirely. The model could not predict fine spectral details, could not explain the relative intensities of spectral lines, and offered no insight into chemical bonding or the structure of the periodic table. It was, in the language of a later generation, a patchwork, a set of quantization rules bolted onto classical mechanics without any deeper theoretical foundation. This period, from roughly 1913 to 1925, became known as the Old Quantum Theory. It was a strange interim. The rules worked in certain specific cases, sometimes with startling accuracy, but they were ad hoc. Arnold Sommerfeld in Munich extended Bohr's model to include elliptical orbits and relativistic corrections, improving the agreement for hydrogen-like systems. Hendrik Kramers, in Copenhagen, developed sophisticated methods for calculating transition probabilities. Each refinement brought new precision, but no one could explain why the rules held. The theory felt provisional, like scaffolding that would eventually need to be replaced by a proper structure. Bohr understood this better than anyone. He had founded his own Institute for Theoretical Physics at the University of Copenhagen in 1921, and it quickly became the intellectual centre of quantum research. Physicists from across Europe, and eventually the world, came to Copenhagen to think, to argue, and to work under Bohr's intense Socratic style of mentorship. The answers were not there yet, but the place where they would be found was being built. While Bohr and his colleagues in Copenhagen were wrestling with the limitations of the old quantum theory, a doctoral student in Paris was about to change the terms of the debate entirely. Louis de Broglie came from an aristocratic family. His older brother Maurice was a respected experimental physicist, and Louis had initially studied medieval history before turning to physics, an unusual path that may have given him a certain freedom to think in unusual ways. In 1924, he submitted a doctoral thesis that contained a single breathtaking idea. If light, which everyone had always treated as a wave, could behave as a particle, then perhaps matter, which everyone had always treated as particles, could behave as a wave. The proposal was not a vague analogy. De Broglie gave it a precise mathematical form. He suggested that every particle, every electron, every proton, every object with momentum has an associated wavelength. The wavelength is equal to Planck's constant divided by the particle's momentum. For anything large enough to hold in your hand, the wavelength is so vanishingly small that it could never be detected. But for something as light as an electron, moving at the speeds typical inside an atom, the wavelength is comparable to the spacing between atoms in a crystal. At that scale, the wave nature of matter should be observable. The thesis examiners were unsure what to make of it. The idea was bold, but it rested entirely on theoretical reasoning. There was no experimental evidence. Paul Langevin, de Broglie's supervisor, sent a copy to Einstein, who recognized the quality of the thinking immediately. On the strength of Einstein's enthusiastic endorsement, the thesis was accepted. De Broglie received his doctorate, and the idea entered the wider physics community. But without experimental proof, it remained a hypothesis, elegant, suggestive, and unverified. It took 3 years for that proof to arrive, and when it did, it came from an unexpected place. At Bell Telephone Laboratories in New York, Clinton Davison and Lester Germer were studying how electrons scatter off a nickel surface. Their experiment was not designed to test de Broglie's hypothesis. They were investigating surface properties of metals for practical applications. But an accident changed everything. A vacuum seal broke, air contaminated the nickel target, and when they reheated it to clean the surface, the nickel recrystallized into large ordered crystal domains. When they resumed their measurements, the scattering pattern had changed dramatically. The electrons were no longer bouncing off in a smooth distribution. They were forming sharp peaks at specific angles, the unmistakable signature of diffraction. The electrons were behaving as waves, and the crystal lattice was acting as a diffraction grating. The wavelengths matched de Broglie's prediction exactly. Davison and Germer published their results in 1927. Independently and almost simultaneously, George Paget Thompson in Aberdeen fired electrons through thin metal foils and observed diffraction rings. The same phenomenon confirmed by a completely different method. Thompson was the son of J.J. Thomson, who had discovered the electron as a particle 30 years earlier. The father won a Nobel Prize for showing the electron is a particle. The son would win a Nobel Prize for showing it is a wave. Both were right. The implications rippled outward immediately. If electrons have wavelengths, then the quantization conditions that Bohr had simply postulated now had a physical interpretation. An electron in a stable orbit is one whose wavelength fits exactly around the circumference. A standing wave, like a vibrating string fixed at both ends. The allowed orbits are those that support whole numbers of wavelengths. Bohr's mysterious rules suddenly had geometry behind them, but de Broglie's wave hypothesis also raised a question it could not answer. What exactly is waving? A water wave is a disturbance in water. A sound wave is a disturbance in air. What is an electron wave a disturbance in? De Broglie himself imagined a real physical wave guiding the particle along its path, an idea he would return to decades later. Others were not so sure. The answer, when it came, would arrive from two very different directions at almost the same time, and the argument over what it meant would never fully resolve. In the summer of 1925, Werner Heisenberg was miserable. He had fled to Helgoland, a barren, wind-scoured island in the North Sea, to escape a crippling bout of hay fever that had left his face so swollen he could barely see. He was 23 years old, a student of Arnold Sommerfeld and Max Born in Göttingen, and he had been struggling for months to find a way past the failures of the old quantum theory. On the island, working through the nights with little else to do but think, he found it. Heisenberg's breakthrough was radical in form as well as content. He decided to abandon any attempt to describe what an electron is doing between measurements. The old quantum theory had tried to picture electrons in orbits, following trajectories, occupying definite positions at definite times. Heisenberg discarded all of it. Instead, he built a mathematical framework based entirely on things that can actually be observed: the frequencies and intensities of spectral lines. The quantities in his theory were not ordinary numbers. They were arrays of numbers, tables that encoded the relationships between different observable transitions. He did not know it at the time, but what he had constructed was matrix mechanics. When he showed his work to Max Born back in Göttingen, Born recognized the mathematical structure immediately. The arrays were matrices, and the rules Heisenberg had discovered by instinct were the rules of matrix multiplication. Born, together with his student Pascual Jordan, formalized the framework into a complete and rigorous theory within months. The theory worked. It produced the correct energy levels for the hydrogen atom. It handled the intensities and transition probabilities of spectral lines that the old theory could not touch. But it was deeply abstract, almost willfully opaque. There were no waves, no orbits, no pictures of any kind, just algebra. Most physicists found it intimidating, and many found it ugly. Less than a year later, Erwin Schrödinger offered something entirely different. Working in Zurich over the Christmas holidays of 1925, inspired directly by de Broglie's matter waves, Schrödinger constructed a wave equation, a single elegant differential equation that described how a quantum wave evolves in space and time. Where Heisenberg had rejected visualization, Schrödinger embraced it. His equation produced wave functions, smooth, continuous mathematical objects that you could picture and plot. The energy levels of the hydrogen atom fell out of the equation as naturally as the harmonics of a vibrating string. It was beautiful, intuitive, and immediately accessible to the many physicists trained in the well-established mathematics of classical waves. The physics community preferred Schrödinger's version overwhelmingly. It was familiar territory. Heisenberg was furious. He wrote to Wolfgang Pauli that Schrödinger's approach made him sick, that the physical picture it seemed to offer was an illusion, a regression to comfortable classical habits. Schrödinger, for his part, found matrix mechanics repulsive. He called it a frightening, even repugnant method. The personal antagonism was real, but it also masked a deeper puzzle. The two theories appeared completely different. Different mathematics, different philosophy, different starting assumptions, yet they gave exactly the same answers. Every energy level, every transition probability, every measurable quantity came out identical. Schrödinger himself proved the mathematical equivalence in 1926, showing that his wave mechanics and Heisenberg's matrix mechanics were two representations of the same underlying structure. Paul Dirac, a young British physicist of extraordinary analytical precision, took the unification further still. His transformation theory demonstrated that both approaches were special cases of a more general framework, that quantum mechanics was a single theory that could be expressed in many different mathematical languages. But equivalence in the mathematics left the deepest question unanswered. What does the wave function actually mean? Schrödinger had hoped it represented something physical, a smeared-out distribution of electric charge perhaps, or a real material vibration in space. Max Born, in a short paper in 1926 that would eventually earn him a Nobel Prize nearly 3 decades later, proposed a different and far stranger answer. The wave function, Born argued, is not a physical wave at all. Its square gives the probability of finding the particle at a given location, nothing more. The wave function does not tell you where the electron is. It tells you where the electron might be and how likely each possibility is. This was a rupture. Physics had always been in the business of predicting what will happen. Now, for the first time, the most complete possible description of a system was saying that it could not. The theory was fundamentally, irreducibly probabilistic. Not approximately, not due to ignorance or incomplete information, but in principle. Einstein hated it. Schrödinger hated it. But the mathematics was unambiguous, and every experiment that tested it confirmed Born's interpretation without exception. In February of 1927, Werner Heisenberg was alone in Copenhagen. Bohr had left for a skiing holiday in Norway, and Heisenberg, still working through the implications of the new quantum mechanics, found himself circling a question that had been nagging at him for months. If the theory is fundamentally probabilistic, if a particle does not have a definite position until it is measured, then what are the actual limits of what measurement can reveal? He attacked the problem with a thought experiment. Imagine trying to determine the exact position of an electron. To see it, you need to bounce something off it, a photon, say. To measure the position precisely, you need a photon with a very short wavelength, which means very high energy. But a high-energy photon, when it strikes the electron, kicks it violently, changing its momentum in an unpredictable way. The act of measuring the position destroys your knowledge of the momentum. Use a gentler photon, longer wavelength, lower energy, and you preserve the momentum. But now the position measurement is blurred. You cannot win. The more precisely you know one quantity, the less precisely you can know the other. Heisenberg formalized this into a mathematical inequality. The uncertainty in position, multiplied by the uncertainty in momentum, can never be smaller than a fixed minimum value. A value set, once again, by Planck's constant. This is not a statement about the clumsiness of instruments. It is not a claim that better technology could overcome the limitation. It is a statement about what nature contains. Position and momentum do not simultaneously exist as definite quantities. The information is not hidden. It is not there. He called it the uncertainty principle, and he published it in a paper in March of 1927. Bohr, when he returned from Norway and read the paper, was troubled, not by the conclusion, but by the reasoning behind it. He felt Heisenberg's gamma-ray microscope argument was misleading. It framed the uncertainty as arising from a physical disturbance, the photon kicking the electron, which implied that the electron had a definite position and momentum before the measurement came along and disrupted it. Bohr believed this missed the deeper point entirely. The issue was not disturbance. The issue was that concepts like position and momentum are only meaningful within specific experimental contexts. An experiment designed to measure position creates a situation in which position is well defined. An experiment designed to measure momentum creates a different, incompatible situation. You cannot design a single experiment that makes both quantities simultaneously precise, because the experimental arrangements required are mutually exclusive. Bohr articulated this view in what he called the complementarity principle, which he presented at a conference in Como, Italy, in September of 1927. Complementarity held that quantum objects possess pairs of properties, wave and particle, position and momentum, that are both real but can never be observed together. They are complementary aspects of a single reality, each complete in its own experimental context, but never simultaneously applicable. The disagreement between Heisenberg and Bohr was not trivial, and it was not merely philosophical. It was a disagreement about what the uncertainty principle means. Heisenberg's version suggested a world where measurement disturbs a pre-existing reality. Bohr's version suggested a world where reality itself is contextual, where the properties of a quantum object depend on how you choose to look at it. The two men argued about it intensely in the corridors and offices of the Copenhagen Institute. Heisenberg, by his own later account, was reduced to tears at one point during these exchanges. Eventually, a working compromise was reached. Heisenberg added a postscript to his published paper acknowledging Bohr's perspective. But the underlying philosophical tension never fully disappeared. What emerged from these months in Copenhagen was not a single, tidy doctrine, but a loose and evolving framework that would later be called the Copenhagen interpretation. Its core commitments were roughly these. The wave function is the most complete possible description of a quantum system. Measurement causes the wave function to collapse into a single definite outcome. The probabilities encoded in the wave function are fundamental, not a reflection of hidden ignorance. And it is meaningless to speak about what a quantum system is doing when no one is looking. Not everyone accepted this. Not then, and not now. But by the autumn of 1927, as the physics community gathered for the 5th Solvay Conference in Brussels, the Copenhagen framework was the position that anyone who disagreed would have to dismantle. And the man who intended to do exactly that was already sharpening his arguments. The photograph is famous. 29 men and one woman, Marie Curie, arranged in 3 rows on the steps of the Hôtel Métropole in Brussels. October 1927. 17 of them were or would become Nobel laureates. It is sometimes called the most intelligent photograph ever taken, and there is a reasonable case for saying it captures the most consequential scientific gathering of the 20th century. The 5th Solvay Conference had been convened to discuss the new quantum mechanics. The organisers, the Belgian industrialist Ernest Solvay's Foundation, had assembled the leading figures in theoretical and experimental physics for a week of formal lectures and, more importantly, informal debate. Born and Heisenberg presented the matrix mechanics formulation and declared, in their joint report, that quantum mechanics was essentially complete. De Broglie presented his pilot wave theory, the idea that particles are guided by real physical waves, as an alternative to the Copenhagen framework. Schrödinger presented his wave mechanics. Bohr spoke on complementarity. But the defining drama of the conference did not happen in the lecture hall. It happened over breakfast. Albert Einstein had come to Brussels with deep misgivings about the Copenhagen interpretation. He did not object to the mathematics of quantum mechanics. He acknowledged that the formalism worked. What he could not accept was the claim that the theory was complete. The idea that nature is fundamentally random, that a particle genuinely has no definite position until someone measures it, struck Einstein as philosophically unacceptable. He was convinced that something was missing, that beneath the probabilities lay a deeper, deterministic reality that quantum mechanics had failed to capture. His method of attack was characteristically elegant. Each morning at breakfast, Einstein would present a thought experiment, a carefully designed scenario intended to show that the uncertainty principle could be circumvented, that position and momentum could both be measured simultaneously with arbitrary precision. Each morning, the other physicists would consider the challenge, and each evening, Bohr would arrive at dinner with a refutation. The exchanges were intense and remarkably focused. Einstein would propose a device, a box with a shutter, a screen with slits, a clock attached to a scale, and argue that it could, in principle, beat the uncertainty limit. Bohr would spend the day analysing the thought experiment in forensic detail and invariably find that Einstein had overlooked some subtle physical effect that restored the uncertainty. The pattern repeated throughout the conference. Einstein attacked. Bohr defended. The audience watched two of the greatest minds in physics testing each other at the highest level of rigour either had ever encountered. One exchange in particular became legendary, though it actually took place at the 6th Solvay Conference in 1930. Einstein proposed a box containing radiation, equipped with a clock-controlled shutter and suspended from a spring scale. By weighing the box before and after releasing a single photon at a precisely known time, Einstein argued you could determine both the energy of the photon and the moment of its emission, violating the energy-time uncertainty relation. It was his most formidable challenge. Bohr was initially shaken. He spent a sleepless night working through the problem. By morning, he had found the answer, and it came from Einstein's own general theory of relativity. The act of weighing the box requires reading a pointer against a scale in a gravitational field. General relativity tells us that a clock's rate depends on its position in a gravitational field. The recoil of the box when the photon escapes shifts the clock's position, introducing an unavoidable uncertainty in the timing. When Bohr worked through the mathematics, the uncertainty was exactly the amount required by Heisenberg's principle. Einstein had been defeated by his own theory. Einstein never accepted the Copenhagen interpretation, but after 1930, his strategy shifted. He stopped trying to show that quantum mechanics was internally inconsistent and began arguing instead that it was incomplete, that it was a correct but partial description of a deeper reality. This shift would lead 5 years later to the most famous thought experiment in the history of physics. De Broglie's pilot wave theory, meanwhile, received a hostile reception at Solvay. Wolfgang Pauli raised a technical objection that de Broglie could not answer on the spot, and the idea was effectively dismissed. De Broglie himself abandoned it and joined the Copenhagen consensus for the next quarter century. The pilot wave would not resurface until a physicist working in a very different political climate gave it new life. What emerged from Solvay was not a resolution, but a hierarchy. The Copenhagen interpretation became the dominant framework, not because every physicist was convinced, but because it worked, and because its most prominent critic had been unable to break it. For the next several decades, questioning the foundations of quantum mechanics would be treated, in most physics departments, as somewhere between unfashionable and career-ending. Einstein's shift from attacking the consistency of quantum mechanics to questioning its completeness culminated in 1935, in a paper that would become the most cited thought experiment in physics. The paper was co-authored with Boris Podolsky and Nathan Rosen, both colleagues at the Institute for Advanced Study in Princeton. It became known by its author's initials, EPR. The argument was deceptively simple. Consider two particles that interact and then fly apart in opposite directions. Quantum mechanics says that certain properties of these particles are correlated. Measure the position of one, and you can immediately infer the position of the other, no matter how far away it is. Measure the momentum instead, and you can infer the momentum of the other. But according to the uncertainty principle, a particle cannot have definite position and definite momentum at the same time. EPR argued that this created a dilemma. Either measuring one particle instantaneously affects the distant particle, violating the principle that no influence can travel faster than light, or the distant particle already had definite values before any measurement was made. If the second option is true, then quantum mechanics is incomplete, There are real physical properties that the theory does not describe. Einstein was not entirely happy with the paper. Podolsky had written it up, and Einstein felt the central point had been buried under formalism. The core idea, as he later expressed it more simply, was this: if quantum mechanics is complete, then measuring a particle here can instantaneously determine the state of a particle there. That kind of action at a distance, what Einstein dismissed as spooky action at a distance, seemed physically absurd. Therefore, quantum mechanics cannot be the whole story. Bohr responded almost immediately with a paper of his own, using the same journal and the same title. His reply was dense and difficult to follow, but the essence was that EPR had made an unjustified assumption about what counts as reality. In quantum mechanics, you cannot talk about the properties of a particle independently of the experimental context in which those properties are measured. The EPR argument assumed that properties exist prior to measurement. Bohr rejected that assumption. Most physicists sided with Bohr, not always because they understood his argument fully, but because quantum mechanics continued to work, and the EPR challenge seemed purely philosophical. That same year, Schrödinger published a response to EPR that introduced two ideas of lasting importance. The first was the word entanglement, Verschränkung in German, to describe the correlation between particles that EPR had identified. The second was the single most famous thought experiment in quantum physics. A cat is sealed in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, the vial breaks, and the cat dies. If it does not, the cat lives. Quantum mechanics describes the atom as being in a superposition of decayed and undecayed until measured. Taken literally, the cat is simultaneously alive and dead until someone opens the box. Schrödinger did not propose this as a serious physical scenario. He proposed it as a reductio ad absurdum, a demonstration that something must be wrong with a theory that allows such a description. The image endured because it made the measurement problem visceral. Superposition is easy to accept for an electron. It is very difficult to accept for a cat. For the next 2 decades, the foundations of quantum mechanics were largely ignored. The war redirected physics toward radar and nuclear weapons. The post-war period brought quantum electrodynamics, transistors, and a culture of pragmatism. The Copenhagen interpretation became orthodoxy not through universal agreement, but through institutional momentum and the overwhelming practical success of the formalism. 2 voices broke the silence. In 1952, David Bohm, an American physicist forced out of the United States during the McCarthy era, published a fully deterministic reformulation of quantum mechanics. Bohm's theory reproduced every prediction of the standard formalism exactly, but it did so using real particles with definite positions at all times, guided by a real wave. It was de Broglie's pilot wave theory made rigorous and complete. The physics establishment largely dismissed it. John von Neumann had published a proof in 1932 that appeared to rule out hidden variable theories entirely. The proof was later shown to contain a subtle but critical error, but by the time that was recognized, the damage was done. 5 years later, a graduate student at Princeton named Hugh Everett proposed something even more radical. Everett suggested that the wave function never collapses at all. Every quantum measurement causes the universe to branch, one branch for each possible outcome, and all branches are equally real. This was the many worlds interpretation. His thesis advisor, John Archibald Wheeler, supported the work but could not protect it from near-total indifference. Everett left physics entirely and spent the rest of his career in defense analysis. His interpretation would not be taken seriously for decades. The foundations of quantum mechanics, it seemed, were a subject that could end careers. The man who transformed the debate from philosophy into physics was working, of all places, at a particle accelerator. John Stuart Bell was a Northern Irish physicist employed at CERN in Geneva, where his official work involved the physics of particle beams and accelerator design. Foundations of quantum mechanics was not part of his job description. It was something he did on the side, during sabbaticals, in the evenings, on his own time. He had been troubled by the questions raised by EPR since his student days, and he was one of the very few physicists of his generation who took Bohm's hidden variable theories seriously. Not because he was certain Bohm was right, but because the mere existence of Bohm's theory proved that von Neumann's impossibility proof was wrong. If hidden variables were not logically impossible, then the question of whether they exist was an empirical one, and that meant it should be possible to design an experiment to settle it. In 1964, Bell published a short paper, just 6 pages, that did something no one had managed in the 30 years since EPR. He made the question testable. Bell's argument was precise and elegant. He considered the EPR scenario: 2 entangled particles flying apart, with measurements performed on each. He asked a simple question. If the results of these measurements are determined in advance by hidden variables, local properties carried by each particle from the moment of their creation, then what constraints does that place on the statistical correlations between the measurements? He derived an inequality, a mathematical ceiling, that any local hidden variable theory must obey. The correlations predicted by such a theory can only be so strong. Then he showed that quantum mechanics predicts correlations that exceed that ceiling. This was Bell's theorem, and its implications were extraordinary. It did not say that quantum mechanics is correct. It said that if quantum mechanics is correct, then no local hidden variable theory can reproduce its predictions. The world cannot be both local, meaning no instantaneous influences between distant objects, and realistic, meaning particles have definite properties independent of measurement. At least one of these assumptions must be wrong. The theorem was a bombshell, but it detonated slowly. The paper was published in a short-lived journal called Physics, which ceased publication just a few years later. Very few people read it at first. The Foundation's community was tiny, and mainstream physics regarded the entire subject with suspicion. Advisors actively warned students away from working on Bell-type questions. It was considered a dead end. Philosophy dressed up as physics. The first people to recognize the experimental potential of Bell's theorem were a small group of physicists who were willing to risk their reputations on it. In 1969, John Clauser, Michael Horn, Abner Shimoni, and Richard Holt reformulated Bell's inequality into a version known as the CH-SH inequality that could be tested directly with existing technology. The original Bell inequality required certain idealized conditions that no real experiment could meet. The CH-SH inequality was designed for the real world, with real detectors and real photon sources. Clauser, a young postdoctoral researcher, was the one who built the experiment. He had been told by senior colleagues that the project was a waste of time, that quantum mechanics would obviously be confirmed, and that no one would care either way. He built it anyway, working with Stuart Friedman at the University of California, Berkeley. Their apparatus used pairs of photons emitted in a calcium cascade with polarization measurements on each photon made at separate detectors. The results, published in 1972, were unambiguous. The correlations between the photon measurements violated the Bell inequality. They matched the predictions of quantum mechanics exactly. Local hidden variables could not account for what was observed. The experiment had real limitations. The detectors were inefficient, they missed most of the photons, which opened what became known as the detection loophole. Perhaps the photons that were detected were not representative of all the photons emitted. The measurements on the two detectors were also set in advance, not changed during the flight of the photons, which left open the locality loophole. Perhaps some unknown signal was passing between the detectors, coordinating the results. These were not trivial objections. They meant that the experiment, while strongly suggestive, was not yet definitive. Closing these loopholes would take another 40 years and some of the most demanding experimental physics ever attempted. But Clauser and Friedman had shown that the question Einstein raised in 1935 was not philosophical. It was physical. It could be measured. And the answer was pointing decisively away from the world Einstein had hoped for. Clauser and Friedman had shown that quantum mechanics was right and local hidden variables were wrong, but science does not work on single experiments, and the loopholes in their test were real. For the result to be definitive, those loopholes had to be closed. Not approximately, not probably, but completely. That effort would span 4 decades and push experimental physics to extraordinary limits. The first major advance came from a young French physicist named Alain Aspect. Working at the Institut d'Optique in Orsay, just south of Paris, Aspect designed a series of experiments in the early 1980s that addressed the most troubling weakness of the Clauser-Friedman test, the locality loophole. In the Berkeley experiment, the settings of the 2 polarization detectors had been fixed before each run. This meant that in principle, some unknown signal could have travelled between the detectors or from the source to both detectors, coordinating the results. The correlations might not be evidence of genuine non-locality. They might simply reflect a shared cause established at the start. Aspect's solution was to change the detector settings while the photons were already in flight. He used acoustic optical switches that could redirect each photon to one of 2 differently oriented analyzers, with the switching happening so fast that no signal travelling at the speed of light could carry information from one detector to the other in time to influence the result. The photons were produced by a calcium cascade source, and the experiment ran at far higher rates than Clauser's, roughly 100 photon pairs per second compared to the earlier experiment's painstaking accumulation over weeks. The results, published in 1982, were decisive. The Bell inequality was violated by a wide margin. The correlations matched quantum mechanical predictions precisely. And with the detector settings changing during flight, the locality loophole was effectively closed. Whatever was producing these correlations, it was not a signal travelling between the 2 sides of the experiment, but effectively is not completely, and experimentalists are precise people. Aspect switches were periodic, not truly random. A determined skeptic could argue that the pattern was predictable. In 1998, Anton Zeilinger and Gregor Weiss in Innsbruck addressed this by using a quantum random number generator to select the detector settings. Each measurement choice was made by a genuinely random quantum process, eliminating any possibility of a predetermined pattern. The Bell inequality was violated again, and the locality loophole was closed more tightly still. The detection loophole proved harder. In every photon-based Bell test, the vast majority of emitted photons are never detected. They are lost to inefficient detectors, misaligned optics, or absorption. If the detected photons are not a fair sample of all emitted photons, the statistics could be misleading. Perhaps the photons that happen to be detected are precisely those that produce quantum-like correlations, while the undetected ones would have restored the classical prediction. This is known as the fair sampling assumption, and for decades no photon experiment could avoid making it. The breakthrough came not from photons, but from electrons. In 2015, Ronald Hansen and his team at the Delft University of Technology in the Netherlands performed a Bell test using entangled electron spins in nitrogen vacancy centers in diamond, one in each of two laboratories separated by 1.3 kilometers. The entanglement was established through a clever heralding protocol. Only when both electrons successfully emitted photons that were detected at a central station was the trial counted. This eliminated the detection loophole entirely. The detector settings were chosen by random number generators, and the separation was large enough that no light-speed signal could connect the two measurements. For the first time, both major loopholes were closed simultaneously in a single experiment. The result? A clear violation of the Bell inequality, consistent with quantum mechanics, with a statistical significance that left essentially no room for doubt. Other groups followed quickly. In the same year, teams in Vienna and at the National Institute of Standards and Technology in the United States performed their own loophole-free tests using different physical systems, and all reached the same conclusion. The debate that Einstein had started in 1935, that Bell had made testable in 1964, and that Clauser had first measured in 1972, was now settled as firmly as any question in experimental physics. In 2022, the Nobel Prize in Physics was awarded jointly to Alan Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. It was a recognition not just of their individual achievements, but of the entire experimental program that had taken a philosophical argument and turned it into one of the most precisely verified facts about the physical world. The experiments are settled. The formalism works. Every Bell test ever conducted has confirmed the predictions of quantum mechanics. And yet the most basic question, what does the theory mean, remains open. This is not a failure of physics. It is a feature of quantum mechanics that has no precedent in the history of science. The theory tells you, with extraordinary precision, what you will measure. It does not tell you what is happening when you are not measuring. Every interpretation of quantum mechanics is an attempt to fill that gap, to provide a story about the world that sits behind the mathematics. And every interpretation so far comes with a cost. The Copenhagen interpretation, in its various forms, remains the most widely taught. Its central claim is that the wave function is the most complete description of a quantum system, and that asking what a particle is doing between measurements is not a meaningful question. Measurement causes the wave function to collapse into a definite outcome. The probabilities are fundamental. This view is pragmatic and has served generations of physicists well, but it raises an obvious difficulty. What counts as a measurement? Where does the quantum world end and the classical world begin? Copenhagen offers no precise answer. The many worlds interpretation, first proposed by Everett in 1957 and largely ignored until the late 1970s, offers a radically different picture. The wave function never collapses. Every possible outcome of every quantum measurement is realized, each in its own branch of a constantly splitting universe. There is no measurement problem because there is no collapse. The cost is ontological extravagance on an almost incomprehensible scale. An infinity of parallel worlds, all equally real, none accessible to any other. Many physicists find this either exhilarating or absurd, and there is no consensus on which response is more appropriate. Bohm's pilot wave theory, also called de Broglie-Bohm theory in recognition of its origins, provides something that neither Copenhagen nor many worlds offers. Particles with definite positions at all times, following definite trajectories, guided by a real wave. The theory reproduces every prediction of standard quantum mechanics exactly. It is fully deterministic. The randomness in measurement outcomes arises not from any fundamental indeterminacy, but from ignorance of the initial conditions, much as in classical statistical mechanics. The cost is non-locality. The guiding wave responds instantaneously to distant events, which sits uncomfortably with the spirit, though not the letter, of relativity. More recent proposals have added to the landscape. Cubism, quantum Bayesianism, treats the wave function not as a description of reality, but as a representation of an agent's beliefs, updated by experience. Relational quantum mechanics, developed by Carlo Rovelli, holds that quantum states are not absolute but defined only relative to a particular observer. Objective collapse theories, such as the Ghirardi-Rimini-Weber model, modify the Schrödinger equation itself, adding a mechanism by which superpositions spontaneously reduce to definite outcomes at a rate that is negligible for individual particles, but becomes overwhelming for large objects. Each of these approaches has defenders, critics, and unresolved technical problems. What none of them has is a decisive experimental advantage over the others. They all reproduce the same predictions. The choice between them is, at present, a choice about what kind of story you find most coherent, which assumptions you are willing to accept, and which costs you are willing to pay. One development has shifted the terms of the debate significantly. Beginning in the 1980s, the physicist Wojciech Zurek and others developed the theory of decoherence, the process by which a quantum system interacting with its environment loses its ability to exhibit interference effects. Decoherence explains why we do not see superpositions in everyday life. The environment constantly measures quantum systems, entangling with them and dispersing their quantum coherence into an effectively irretrievable tangle of correlations. This is not the same as collapse. Decoherence does not select a single outcome, but it explains the appearance of collapse, and it has become an essential tool in every modern interpretation. The measurement problem remains the deepest unsettled question in the foundations of physics. It is not likely to be resolved by a single experiment or a single paper. It may require new physics, a quantum theory of gravity perhaps, or a deeper understanding of the relationship between information and reality. Or it may turn out that the question itself needs to be reframed. The history of quantum mechanics, if it teaches anything, is that the most productive advances have often come not from answering the existing questions, but from discovering that the questions were wrong. In December of 1900, Max Planck stood before the German Physical Society and, without entirely meaning to, opened a door that physics has never been able to close. What lay on the other side was not the orderly, deterministic universe that 19th century science had built and believed in. It was something stranger, a world where energy comes in packets, where particles behave as waves and waves as particles, where the act of measurement changes what is measured, and where two objects separated by any distance can remain connected in ways that no classical theory can explain. The story we have followed across these chapters spans just over a century. It begins with a man trying to fix an equation and ends with a Nobel Prize for proving that the universe is not locally real. Between those 2 points lies one of the most extraordinary intellectual achievements in human history, built not by one mind but by dozens, not in one moment, but across generations of argument, experiment, and revision. Some things are now settled beyond any reasonable dispute. The quantum formalism works. Its predictions have been confirmed to a precision that has no parallel in any other branch of science. In some cases, theory and experiment agree to more than 10 decimal places. Entanglement is real and has been verified in experiments that close every known loophole. the Bell inequality is violated. No local hidden variable theory can account for the observed correlations. Nature, at its most fundamental level, does not behave the way classical intuition says it should. That is no longer a matter of opinion. It is one of the most firmly established facts in all of physics. Other things remain genuinely open. The measurement problem, what happens when a quantum superposition becomes a definite classical outcome, has no universally accepted solution. The interpretation of the wave function is still debated, with serious physicists holding positions that range from the wave function is everything and the universe splits to the wave function is nothing more than a bookkeeping tool for personal expectations. Quantum gravity, the unification of quantum mechanics with general relativity, remains one of the great unsolved problems in theoretical physics, and it is entirely possible that resolving it will require revisions to quantum theory itself. The practical limits of quantum computation, quantum communication, and quantum sensing are still being mapped, and the gap between theoretical promise and engineering reality remains large. What strikes me most, looking back across this history, is the human thread running through it. Planck's deep conservatism, which led him to a revolution he never intended. Einstein's stubbornness, which kept him questioning the foundations long after most of his peers had moved on, and which turned out decades later to have been asking exactly the right questions. Bohr's relentless, almost maddening insistence on precision of thought. De Broglie's boldness and subsequent retreat. Heisenberg's fierce ambition and equally fierce insecurity. Schrödinger's elegance and his frustration at what his own equations seemed to imply. Bell's quiet, patient brilliance, working on the margins of respectable physics and producing one of the most consequential results of the 20th century. Clauser building an experiment his colleagues told him was pointless. Aspect, Zeilinger, and Hansen spending years closing loopholes that most physicists thought were academic. None of these people set out to build the theory we have now. They set out to solve specific problems, to fit a curve, to explain a spectrum, to resolve a paradox, to close a loophole. The theory assembled itself from their individual efforts, often in directions none of them anticipated or wanted. That is perhaps the most honest thing to say about quantum mechanics. It was not designed. It was discovered, reluctantly, piecemeal, and against the preferences of many of its own creators. The universe did not ask for our approval. It simply turned out to work this way. And the fact that we can describe it at all, in a mathematical language of extraordinary precision, built by people arguing with each other across decades and continents, is itself something worth pausing to appreciate. We began with a man who did not want to be a revolutionary, standing before an audience that did not know it was witnessing the start of something that would reshape every corner of physics. We end with a theory that is at once the most successful and the most unsettling in the history of science. We are still arguing. The questions have not run out. That, more than anything, is why this story is worth telling. Not because it is finished, but because it is not.